Alright, so today I'll be doing the LONCAPA video solution from problem set 7, and it's the bump in the road. So, the question is, you're driving your car over a circular shaped bump in the road that has a radius of curvature of 62.4 meters. If the car is traveling at a constant speed of 14.5 meters per second, calculate the apparent weight of your 62.2 kilogram passenger as you pass over the top of the bump. Alright, so we're just going to draw a picture really quick of what's happening here. So we know we have a bump in the, let me draw that a little bit lower. We have a bump in the road. And so beneath this bump, we can imagine it as a circle. That's what's causing that curvature. So here is our car. And inside we have our little passenger. So from the problem, we know that the passenger is 62.2 kilograms. The car is moving at a speed of 14.5 meters per second. And then our radius is going to be 62.4 meters. So now that we have our picture drawn, the part A, we are looking for apparent weight. So apparent weight is equal to real weight minus mass times acceleration. So I'm just going to kind of box that so it's off to the side, and we can reference that as we start this problem. So the acceleration piece of this is actually just going to be gravity, because if we think again about our acceleration vectors, they all point radially inwards, which is going to be the same as gravity if you were to draw the free body diagram. So we're just going to change this A into G. So this gives us the equation mv squared over r is equal to mg minus n. We can rearrange that to get n is equal to mg minus mv squared over r. And now it's just a matter of plugging in values. So our force is equal, or our apparent weight is equal to 62.2 times 9.81 minus 62.2 times 14.5 squared all over 62.4, which this first part of the equation, 62.2 times 9.81, is going to give us 610.182. The second part of the equation will give us 209.576. And so altogether, that's going to equal 400.6 newtons as our apparent weight for the problem. Moving on to part 2, what is the maximum speed that you can drive the car over the top of the bump without losing contact with the road? So, without losing contact, the force of the uniform circular motion, so by this, I mean the force of the car traveling over the bump, because as you can see up here, back from part 1, our drawing, the car is tracing this path at a constant speed. So that's how we know it's uniform circular motion. So just the force of the car traveling over the bump cannot exceed the force of gravity. Because clearly we can't have our car flying over the road. If the force of the car exceeds gravity, then it's going to end up flying off the road and it's going to end up losing contact. So this can be written as the force of uniform circular motion. That equation is mv squared divided by r, and then it has to equal, because we're looking for maximum speed, so it can equal the force of gravity, it just can't exceed it. So we're going to have mv squared over r is equal to mg. So let's rearrange these variables. Let's see, we have mv squared is equal to mgr, and now we can divide by m on both sides, so we have v squared is equal to gr. And so since we're solving for speed, as we've already mentioned, this is going to be the variable that we're solving for. So we have v squared. Again, this is just a matter of now plugging in numbers. So v squared is equal to 62.4, which was our radius. So 62.4 times 9.81, and then obviously we're gonna do the square root of both sides, and our final answer comes out to be 24.7 meters per second. So yeah, that would be how you solve this bump in the road problem. You first draw your diagram. We know that the force of gravity is going to be the acceleration part of this apparent weight equation. Also this, I forgot to mention earlier, this mv squared r is going to be your uniform circular motion force, so that's the real weight, minus the mg that we calculated. So yeah, that's how you would do this problem, and hopefully that helped.